Okay, this is section 9.1. This is number 64. And it says differentiation, use differentiation to find a series for f of x equals 2 over 1 minus x all to the third power. So how are we going to use differentiation for this? Okay, so what you have to do is find what we're going to take the derivative of to get this. And hopefully we have a series for that. So what I did was I took the antiderivative of this, and then I put this up on the top, so I had 2, 1 minus x to the negative 3. And if I'm going to take the antiderivative of that, I have to have u to the n du. I have to have a negative for that, so I had a negative out here and a negative in front. And then when I take the antiderivative, I can keep the 2 in front and the negative, and then I can add 1, so it's going to be negative 2 divided by negative 2's. These cancel, so I end up with this, which is this. So if the antiderivative of my function that I want is 1 over 1 minus x squared, then the derivative of this is this. Now I do have a series for this, and this was example 4 on page 477. If you look on the bottom, you'll see that this series ends up being this. 1 plus 2x plus 3x squared, etc. That again is on the bottom of page 477. All right? And we got that series by differentiating 1 over 1 minus x. All right? So by differentiating 1 over 1 minus x, we got this one. All right? So now we can differentiate this one, and we'll get this 2 over 1 minus x to the third. All right? So that equals the derivative of this. So I'm going to take the derivative of this series. So if I take the derivative of this series, I can do it term by term. That's easy. That's going to end up being 0, 2, 6x, 12x squared. And then if we go to the general term, that's why it's handy to have the general term. The derivative of the general term is the n stays there. I multiply by n minus 1, and this becomes n minus 2. So this was my expansion for this 2 over 1 minus x to the third. Now this is kind of funny because we don't usually like this in the general term. It's going to be kind of hard for our index. So if we replace n by n plus 2, so we just move everything over. All right? So instead of n, we just move everything, shift everything over 2. If we put n plus 2, that's n plus 2 minus 1 is n plus 1, and this n plus 2 minus 2 is n. That's going to be a little bit easier to write the general term. And this will be the general term, so it's going to be the index of e's that are set up. So the index is going to go from 0 to infinity of n plus 2 times n plus 1 x to the n. And this will have the same interval of convergence as we did on page 477, which was the same interval of convergence of the original function, which was 1 over 1 minus x. That interval of convergence was between negative 1 and 1, because that was just the original. If you look on the bottom, page 477, example 4, you see that we started with 1 over 1 minus x, which is just the geometric series. My ratio is negative x, so that's going to be between negative 1 and 1. That's the interval of convergence. So this function that we got had the same interval of convergence. All right? So therefore this one has the same interval of convergence, because we're still just taking the derivative of these series. Okay? So that was number 64. It might be a nice idea to write down some of these ones that we do find, that we do differentiate, because then we'll be kind of using them over and over again to generate new series. And that's what they ask you to do on the AP exam on some of the free response questions. Hope those help.